Section 10.20, Facial Recognition. Suppose we have grayscale images of 1,000 faces, and we reduce the resolution of each image to only 3 pixels. The facial images can then be represented by vectors, or points, pi, for I from 1 through 1,000 in the unit box in R3, as in this figure right over here. So let's pick 10 face vectors, these guys, as our training set, and these are the blue dots in the figure. So we're just going to take 10 out of the 1,000 to use as a training set for facial recognition. So we take these 10, and in order to start, we'll have to find the mean of this training set, and we'll use that mean to find caricature vectors, which are vectors that represent the distance from the mean for each of these vectors. So first we'll calculate the mean, m vector, by just taking 1/10 of the sum of these vectors, because there's 10 of them. So 1/10 of p1 plus p2, and so on, through p10. That'll give us the mean vector. And using a calculator, I got 0.5076, 0.4877, 0.6041. So then each of the caricature vectors q for I from 1 through 10 will be equal to pi minus the mean vector. So that gives us q1 equal to 0.2196 negative 0.2051 0.1363 just by taking p1 minus m. So now we'll get q2, take p2 minus m, and we get 0.1687 negative 0.1388 0.0998. Let's get q3 now. So that's 0.0355 negative 0.0137 negative 0.0285. For q4, we have negative 0.3651, 0.3949, negative 0.3240. And for q5, we'll get negative 0.2042, 0.1763, negative 0.0801. Now let's get q6. So that's 0.0730, negative 0.0723, 0.0688. For q7, we'll get negative 0.0128, 0.0473, negative 0.0095. For q8, we get 0.1594, negative 0.1491, 0.1344. For q9, we get negative 0.1581, 0.0999, negative 0.1061. And last but not least, q10. That'll be 0.0740, negative 0.1397, 0.1091. Okay, so now we got our caricature vectors. What we have to do next is find the 3x10 caricature matrix Q, the 3x3 correlation matrix C, given by Q times Q transpose, and the 10x10 matrix Q transpose Q. So Q is just the matrix that's built out of each of these vectors as a column of Q. So Q1 starts as 0.2196, then negative 0.2051, and then 0.1363. Oh, oops. I have to just start that as the column, and then the second column is given by Q2, so that's 0.1687, negative 0.1388, 0.0998. Right, just by reading off Q2. And I'll keep going in this fashion until I get all 10 of the Qs. Next, I use the calculator to get C, the matrix given by Q multiplied by Q transpose, as 0.3143, negative 0.3049, 0.2318, negative 0.3049, 0.3077, negative 0.2348, 0.2318, negative 0.2348, 0.18, sorry, 68. And then A, given by Q transpose Q, is this monstrosity that I managed to write out with a calculator. So I'll just fill that in over here. Whew. Now you know why we only used 3 pixels for each of the images. Let's now find the eigenvalues lambda 1, lambda 2, lambda 3, and corresponding normalized eigenvectors of this correlation matrix. Again, I just used a calculator for this. It'd be way too difficult to do by hand. First eigenvalue is 0.7949, and corresponding eigenvector is 1.3069, negative 1.2998, 1. And then normalized, this becomes 0.6232, negative 0.6198, 0.4769. Next is lambda 2, given by 0.00, or actually, sorry, 0.0105, eigenvector negative 1.0116, negative 0.24771, which we then normalize to get negative 0.7006, negative 0.1716.6926. And last but not least, lambda 3 given by 0.0034, v3 as 0.6420, 1.141491, normalized to become 0.3474, 0.7658, 0.5412. Let's now find the 10 eigenvalues of the matrix A and verify that the eigenvalues lambda 1, lambda 2, lambda 3 of the matrix C in part C are the non-zero eigenvalues of A, and that corresponding eigenvectors are Q, U1, Q, U2, and Q, U3, with norms given by the square roots of the eigenvalues. In this example, it's easier to work with the 3 by 3 matrix C rather than the 10 by 10 matrix A. However, that's not usually the case. This is just because we used a very small training set. In most facial recognition applications, it turns out that A will be much smaller than C. In any case, here are the lambda 1, lambda 2, lambda 3. Let's write them out. Lambda 1 is 0.7949, and it gives us vector v1. I'll write out the entries. 1.7808, 1.2923, 0.0920, negative 3.3926, negative 1.4871, 0.6665, negative 0.2264, 1.3850, negative 1.1423, 1. Okay, so that's V1. And normalizing gives us U1, given by 0.3690, 0.2678, 0.0191, negative 0.7030, negative 0.3081, 0.1381, negative 0.0469, 0.2870, negative 0.2367, and 0.2072. Okay, so that was all for the first eigenvalue. Let's do the second one now for lambda 2, given by 0.00, or I did it again, 0.0105. Okay, so then that one gives us eigenvector v2, given by negative 0.5097, negative 0.5251, negative 0.8986, negative 0.7695, 1.2066, 0.1857, negative 0.1219, 0.1421, 0.43381, and we normalize that to get U2, given by negative 0.2364, negative 2435, negative 0.4168, negative 0.3569, 0.5596, 0.0861, negative 0.0565, 0.0659, 0.2012, 0.4638. Okay, one left to do for lambda 3. That one was 0.0034, and this gives us a V3 of 0.3064, negative 0.2586, 0.5817, 0.0037, negative 0.9303, negative 0.3491, negative 1.1542, negative 0.6276, 1.57161. Okay, let's normalize that to get U3. So that's 0.1185, negative 0.1000, 0.2250, 0.0014, negative 0.3599, negative 0.1350, negative 0.4465, negative 0.2423, 0.6080, 0.3868. Okay, so that's U3, make a little equal sign. And we were supposed to check that if we could take Q times U1, Q times U2, and U3, that the length is the square root of the eigenvalues. So let's do that. Q times U1 is 0.5557, negative 0.5526, 0.4252, and let's go back up. We can see that QU1 is not the same as the U1 we had before. However, it does still work as an eigenvector. Not all eigenvectors be the same. And if we take the length of QU1, then it turns out it does actually equal the square root of lambda 1 because it is equal to 0.8916. And let's do the same thing for QU2. We get negative 0.0717, negative 0.0177, 0.0707, and looking at the length of QU2, that does turn out to be the square root of lambda 2, which is 0.1025. If we look at QU3, then that's negative 0.0201, negative 0.0449, negative 0.0318, and the length of QU3 is equal to the square root of lambda 3, 0.0583. let's now compute the three eigenfaces determined by the training set. The eigenfaces are just QU1, QU2, and QU3, so we'll just list them. So E1 is QU1. I'll just copy it. So that's 0.5557, negative 0.5526, 0.4252, E2 is QU2, which is negative 0.0717, negative 0.0177, 0.0707. E3 is QU3, and that'll be negative 0.0201, negative 0.0449, negative 0.0318. And now we have to compute the three features of the 10 faces in the training set. So that's not too hard. We just have to take each of the features Fij will be equal to the caricature Qi transposed multiplied by the face Ej divided by the eigenvalue lambda j. So for the first feature, F1, we'll build that out of, it'll be the vector with entries F11, F12, F13. So plugging in, that's Q1 transpose times E1 divided by lambda 1 for the first entry, then Q1 transpose E2, because it's I for the Q's and J's for the E's and lambdas, so E2 divided by lambda 2, and then Q1 transpose E3 divided by lambda 3. So we get 0.3690, negative 0.2361, 0.1355. And we just keep doing this. So for F2, we'll take F21, F22, and F23 and put them together and get 0.2678, negative 0.2460, negative 0.0978. For F3, we'll get F31, F32, F33, and that'll be 0.0191, negative 0.4112, 0.2376. For F4, that's F41, F42, F43, given by negative 0.7031, negative 0.3542, negative 0.0263. F5 is F51, F52, F53, negative 0.3082, 0.5579, negative 0.3718. F6 is F61, F62, F63, given by 0.1381, 0.0866, negative 0.1203. Then we have F71, F72, F73, and that'll be negative 0.0367, 0.0716, negative 0.6378. And then for F8, F81, F82, F83, given by 0.2870, 0.0678, negative 0.2304. For F9, we have F91, F92, F93, given by negative 0.2367, 0.1968, 0.6077. And finally for F10, we have F101, F102, and F103, given by 0.2072, 0.4648, 0.3870. So now we could actually run facial recognition because we have the features. We just take a picture and we compare it with the features by taking the distance of that picture vector with the features. So to demonstrate this, let Fij denote the jth feature of the ith face vector. So the ith caricature vector is given by Qi, Fi1 times E1, Fi2 times E2, Fi3 times E3. And let's suppose that Qi is approximated by just a Fi1 E1, so we'll just discard the rest of it to make the computation of Qi easier. Okay, so each character vector is going to be approximated by the feature corresponding to the largest eigenvalue. Let's find the Euclidean distance between each caricature vector and its approximation. In the figure, the orange line passes through the average coordinates of the 1,000 picture points and lies in the direction of the eigenface. So the distances computed in this part are the distances of the blue training set points to the line. So we have these blue training set points over here. We're about to just compute the distance to that orange line. Okay, let's do it. So first, let's get the distance between Q1 and its approximation F11E1. And that'll be 0.0145 squared plus negative 0.0012 squared plus negative 0.0206 squared with the square root. And we get 0.0252, which is very small, as we'd expect. Let's keep going, get all of the distances. So for Q2 minus F21E1, that'll be 0.0199 squared plus 0.0092 squared plus negative 0.0141 squared square root, and that's 0.0261. for Q3 minus F31 E1, we get 0.0249 squared plus negative 0.0031 squared plus negative 0.0366 squared, square root, and it's 0.0444. Next up, Q4 minus F41 E1. So 0.0256 squared plus 0.0064 squared plus 0.0250 squared, 0.0363. Then for Q5 minus F51 E1, we get negative 0.0329 squared plus 0.0060 squared plus 0.0509 squared. So it's 0.0609. Then we have Q6 minus F61 E1, and that's negative 0.0037 squared plus 0.0040 squared plus 0.0101 squared. And we get 0.0115. Let's keep going. For Q7 minus F71 E1, we get 0.0076 squared plus 0.0270 squared plus 0.0061 squared. And the square root gives us 0.0287. Next up, Q8 minus F81 E1, and that's negative 0.0001 squared plus 0.0095 squared plus 0.0124 squared, and that becomes 0.0156. Then Q9 minus F91 E1 is negative 0.0266 squared plus negative 0.0309 squared plus negative 0.0055 squared, and we get 0.0411. For Q10 minus F101 E1, we get negative 0.0411 squared plus negative 0.0252 squared plus 0.0210 squared, and that's 0.0526, which is small just like all the rest of them.